Let's review for the Unit 4 exam, and it's all about force and Newton's laws. So let's review Newton's laws of motion. There's 3 of them. And I do want you to know the 3 laws and be able to explain them briefly. The first law is the law of inertia. And I'm not going to write everything down I'm going to say because it would take too long. The law of inertia. Basically, the law of inertia is things don't change the way they're moving unless you force them to. So, for example, if you were to throw a baseball out in space, let's say you throw a 90-mile-an-hour fastball, but you're out in space. There's no gravity, there's no planets around, there's nothing like that. No asteroids. You throw that baseball, it's going to go in a straight line at 90 miles per hour forever. Well, maybe not forever, but it has to, maybe it gets too close to a planet and the gravity will change its trajectory because there's a net outside force acting on it. But that's a force. So and what forces do is they change the motion of objects. So that's the law of inertia. Things don't change the way they're moving unless you force them to. Now, the second law is the law of acceleration. And it is described by this equation. If you add up all the forces acting on an object, that's equal to we call that the net force. So we have to add all the forces. When I add up all the forces on an object, the force that's left over, after you've canceled out stuff and everything, or some things make forces bigger, smaller, whatever, that's the net force. And that net force will cause an acceleration. And there is a direct proportion between the net force and the acceleration. The greater the force, the greater the acceleration. But the amount of acceleration depends on how much inertia an object has. And the way we measure inertia is with mass, m. So we get the famous equation, F equals ma. The direction of the acceleration will be in the same direction as the net force. Okay, and so we worked a lot of problems involving that. Come on in. Come on. Yeah. What's this? For me? Oh my gosh. Okay. I'm recording this. Well, I don't know how much posterity is going to watch this, but sixth period will watch this. And I just wanted to see what I got. I'm recording this right now. See, so look, there we go. So you may not be able to understand much of what. Thank you. You're awesome. You are a great human being. Now I can eat it from all of them. We'll learn about potential energy and stuff later. All right.
Are you happy with yourself?
Are
you happy with what you're doing right now?
I'm so happy right now. I was miserable about 2 minutes ago, but now, yeah. Okay, number 3 is the law of interaction. And the force of 1 on 2 is equal, but in the opposite direction, as the force of 2 on 1. Now that's the mathematical way of saying it, but for every force on one object, there must be an equal and opposite force on another object. The objects don't have to be touching, like the moon and the earth, the gravity between the moon and the earth. The moon pulls on the earth with just as much force as the earth pulls on the moon. Okay, and that's true for everything. The earth pulls you down, you pull the earth up. You're standing on the floor, pushes you up to support your weight, but you push down on the floor with an equal and opposite force. That's true for everything that we see in the universe. There's no exception to this because we've never observed one. All science is essentially empirical. The day we see an exception to this law, we can't call it a law anymore, or we have to modify the law. But we haven't seen an exception to that yet.
We
So
also haven't seen a black hole.
you want even a black hole obeys these three laws.
They don't exist.
Okay. Okay, now I'm miserable again. I was happy. Okay. Then we went over a two-step or a five-step procedure. I said, remember the procedure. Okay, this was we're going to use these ideas, these Newton's laws, to solve problems, and one of the problems is, you use this procedure to solve these problems. And the first step, of course, is, hey, you're going to have to do this on the test. Given, find, solve with sketch. Am I on screen? Yeah. Well, it's kind of small, though. Let me zoom in. Okay, given, find, and solve with the sketch. You're going to have to do that for, I think there's 6 problems on the test. One of them is kind of a conceptual question. The others are problems. And I want to see you using these, the procedure. Given, find, and solve with the sketch of the problem. Number 2, if it involves force, and you're going to have the acceleration, you got to draw the free body diagram. Okay. Now, step 3. See, forces are vectors, and they can be in the x direction or the y direction. Now, the next unit, we're going to talk about forces when they're not lined up. When they're like a force could be like 50 newtons at 30 degrees from the horizontal. So we're going to learn how to deal with that. But for this unit, everything's going to kind of either be in the x direction or the y direction. So you have to establish what's your x direction and what's your y direction. And it depends on the problem. Sometimes you want positive y to be down. Maybe you'll want x to be to the left. You can do that. As long as you stay consistent with that through the whole problem, you'll be all right. And then 4, you think once you've got your free body diagram drawn and you've identified your x and y directions, then you can sum the forces in the x direction equals ma in the x direction. You just look on the free body diagram and say, what are the forces just in the x direction? And add them together. And set that equal to mass times acceleration in the x direction. Now, maybe you'll have a problem where it tells you, hey, the velocity is constant. What does that mean? If the velocity is constant, then the acceleration is 0. So when you add all those forces together, you set them equal to 0. But if there is acceleration, then it's just one of your variables in your equation now. Then you can do the same thing in the y direction. Now, some problems will only involve the x direction, and the y direction is irrelevant. Sometimes the opposite is true. Like on the exam, you're going to have an elevator problem. Somebody's standing in an elevator, and it's just like the one that was in the homework. Someone's going to be accelerated up or accelerated down, or they're moving up or moving down. You got to really keep track of the difference between acceleration and velocity, right? If the elevator is moving up with constant velocity, you're moving up, but what's true about your acceleration? It's 0. What if you're moving up but slowing down? If you're going up but you're slowing down while you're going up, your acceleration is negative. If you're going down, the velocity is downward, but then you slow up. What's the direction of your acceleration? If you're moving down, but you're slowing down while you're moving down, you're going down, the elevator is going down, but you're slowing down at the rate at which you're going down, your acceleration is positive. Don't think that because acceleration is positive, that always means you're speeding up. Not true at all. If your velocity and acceleration vectors are opposite in direction, you're slowing down. If your velocity and acceleration vectors are in the same direction, you are speeding up. It's that simple. Okay, so you got to keep, that's why you have to do this to keep track of what's positive and negative when you put the numbers into your equations. All right, and then step 5 is math it out, okay? Math it out. You're just going to use algebra to solve for the unknown. Solve for unknown. Okay? So this is the process you're going to use to solve problems on the take-home test, on the exam, and everything else. Now, there are some equations that we developed. If I know an object's mass, gravity's going to pull on it, right? And gravity, the force of gravity is the object's mass times g. And what is g equal to? Yeah, negative downward 9.8 newtons per kilogram. Why do I call it newtons per kilogram? Because you're not necessarily accelerating at 9.8 meters per second squared. But if an object is in free fall, right, if you drop an object, then the only force acting is the force of gravity. Well, this mg will be equal to ma. So g becomes a, and so the 9.8 newtons per kilogram becomes 9.8 meters per second squared. Okay. We also have this. The force of friction equals mu times the normal force. And remember we had mu static. That's if the surfaces are not sliding with respect to each other. Or you have kinetic friction where the two surfaces are sliding with respect to each other. Yes?
So do you drop the lowest test score every semester or every year?
Every semester, but I do not drop the last exam of the semester.
Okay.
So so yeah, I mean, this could be, but you don't want this. This one is actually pretty doable, you guys, if you follow what I'm doing here. All right. So anyway, these, now, so really, these two equations, don't think of these as equations, think of them as instructions on what to do. And then these guys here, you have to know this. If you know this process and these equations, you pretty much can do every problem on the test. You just have to apply it. Okay. So I think we're ready to, let me discuss the individual problems with you. No peeking if you're in the front row. This is the test. Put that camera down. All right. Well, okay. I'll draw a few pictures. And some of them are going to start off pretty simple. And then they're going to get, some of them are a little bit more complicated. What if I've got a crate on a horizontal surface, but I'm going to put wheels on it. And what if it's got someone pulling on it like this, call this F1, and someone pulling on it like this, that's F2. Okay? Can you use this procedure to figure out what the acceleration is? Oh, and one thing, I forgot to I'm going to go ahead and put it on here because you're probably going to make your equation list. You should be keeping, ideally you keep an equation list that you use throughout the year. So you just keep adding to it as we go through each unit. That would be the smart thing to do. But if you're making a new equation list for this exam, you should put, what are these? Yep. Am I still on screen?
Yeah.
So you're going to need the kinematic equations, because what you want to do is you want to, I'll give you a problem where you use force to figure out the acceleration, and then you can use that acceleration with the kinematic equations. Or I'll give you kinematic information, and you have to solve for the acceleration with kinematics equation, and then apply that into the force equation to figure out what one of the forces are. Okay? Or is. Yeah. So, for example, what if I gave you a problem? I've got a couple of forces. And what if I gave you the information to figure out the acceleration? Well, you know what MA is. So if I were to apply the procedure to a problem like this, well, this is given. And, maybe I'll give you the mass. I'll give you, there's other things to give, the initial velocity, the final velocity, whatever. But when you find, you're going to, well, I can find the acceleration. Or maybe I'll give you the acceleration in F2 and you have to find F1. Or, some combination. Maybe I'll give you the acceleration F2 and F1 and you have to figure out what the mass is. It doesn't really matter. I mean, you set up the problem the same way. Given, find, and then solve. Well, draw the free body diagram. Draw the free body diagram separately from the sketch. Here you just kind of show the situation, but here we got to show all the forces, right? We've got m times g, right? That's the force of gravity. We've got normal force like this. We've got F1. We've got F2. Okay, and these are all the forces acting on the object. Hey, even if you screw the problem up, if you do this right, you're going to get credit when I grade the test. Use the procedure on every problem. Or attempt to use the procedure in every problem to maximize partial credit. So if you mess a problem up, you'll still get lots of points if you do this. But if you do this, you're less likely to make mistakes. So I'm going to say, okay, step 3, here's the x direction, here's the y direction. Step 4, let's sum the forces in the x direction equals ma in the x direction. Okay, let's do that. I've got, what's in the x direction here? I've got F1 minus F2. Why is it minus? Because F2 I drew in the negative x direction. So now that I've made it minus, we're just solving for the magnitude of it. We know that it's to the left. Equals ma. And yeah, there is acceleration in this problem in the x direction. So now I can use this equation with step 5 to solve for whatever unknown I have. But you just might need to know this. Sum the forces in the y direction equals ma in the y. What are the forces in the y direction? Well, we've got the normal force minus the weight equals. Now, in a problem like this, is there any acceleration in the y direction? No. So just set it equal to 0. And all this does is tell you that the normal force is equal to the weight. And if it's a problem that's this simple, you can just look at it. Okay, there's no acceleration, so this force and this force have to be equal and opposite. Are we good? Good, 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 good. All right. So you'll have a problem. The problem number 1 is very similar to this. And then problem number 2, I take a problem similar to that, but now I take the wheels off. So if I take the wheels off, what's going on? So I've got some applied force. Maybe I've got some known acceleration and a mass. So now I've got friction. So if I draw the free body diagram, it's given, find, and solve, then draw the free body diagram. I've got this applied force. Whoops. I've got an applied force. I've got gravity. I've got a normal force. And then I've got force of friction. And so if I sum the force in the x direction, and take the time to write this out the way I am, you will get more partial credit if you make a mistake. FA minus FF equals MA. And if I do the same thing in the y direction, right? I've got the normal force minus mg equals 0. Now, I said in the equation list I gave you, remember I said that, the weight, the force of gravity is equal to mg. So usually I'll just write it out as mg. But what's the force of friction equal to? Mu times the normal force. So you use this idea right here, say, oh, how hard are these surfaces being pressed together? Well, that's the normal force. Well, this surface has to support the weight of that crate. So the normal force is just equal to the weight. And then mu will either be given, or you'll be trying to find it, equals the force of friction. So you plug that in there and solve for whatever your unknown is. Maybe the unknown is mu. How do I find mu? Well, if mu is not given and you got to find it, mu is equal to the force of friction divided by the normal force. So, hey, that tells me I got to find the force of friction and I got to find the normal force. What if I don't give you the mass in a problem? Guess what will happen if I don't give you the mass? It's going to cancel out. Either that or I really screwed up. If you're panicked because I didn't give you the mass on a problem, make one up. Pretend, oh, it's 10 kilograms. Why 10? Because the math is easy. And then you can do that, and then you will find out that, oh, that 10 kilograms will cancel out.
So the normal force is always going to be 9.8 if there's no y.
No, mass times 9.8. Yeah.
And then it'll just...
Because the normal force, yeah, if you have more mass, you're going to have more normal force supporting your mass. Okay? Because you have more weight. So take the mass and multiply it by g. For a problem like this, yes, the normal force will always be equal to the weight. Now, in the next unit, we're going to do problems that are a little more complicated, where the normal force is going to be different than the weight. But for right now, you can consider it to be the weight. Well, actually, I lied, because the next problem, problem 3, is an elevator problem. So this is problem number 2. Something like this. Yes?
Can you skip the paper?
Oh, yeah, I'm sorry. Thank you. Okay, problem number 3. Well, we've got an elevator problem. So suppose, so I'll put number 3 down here. So I'm going to have some dude standing in an elevator. And this elevator is going to have a spring scale on it. So you can measure the force between your feet and the... Here's a guy standing there. I always wear a hat. All right. So he's standing there on the spring scale. And he's looking down. Now, if we draw a free body diagram of this dude, let's just draw the dude as a dot just to make it a little bit easier. What forces are acting on this dude? Well, Earth's gravity. How come the dude isn't falling towards the center of the Earth? Because there's a normal force. Now, what do spring scales actually measure? If you stand on a spring scale, it is not measuring your weight. The spring scale measures the force between the normal force between your feet and the scale. If you are not accelerating, that normal force will be equal but in opposite direction to your weight. So when you stand on a spring scale and then you stop and you wait for it to settle down, now that normal force from the spring scale is equal to your weight. But start flapping your arms up and down. Now you're accelerating mass up and down, and you will see that the spring scale kind of wiggles around a little bit. You are not gaining and losing weight while you flop your arms. Okay? You're not getting skinnier and fatter and skinnier and fatter and skinnier and fatter. No. Your weight is constant. Your weight is m times g, but the normal force is changing. And so you can say, oh, let's make up positive. So here's the free body diagram. I've identified my x and y direction. Just to be complete, I'll put x, but you don't really need an x direction there. And now we can sum the forces in the y direction equals ma in the y direction, right? This is step 4. And when I look at this problem, I go, okay, the normal force, which is being measured by the bathroom scale, minus mg is equal to ma. Now be careful. If I give you an acceleration, if the acceleration is down, you better put that negative in there or you'll get the wrong answer. Okay? So, and notice that if your normal force is equal to your weight, then this will be equal to 0. You're not accelerating. And you feel normal. And that can be happening while the elevator's going up or while the elevator's going down. You can have constant velocity and you will feel normal. But let's say you're at the bottom of the elevator and it accelerates up. If the acceleration is up, if you have positive acceleration, well, which one of these forces has got to be bigger? Well, your normal force has to be bigger because you're accelerating up, so you haven't needed an upward net force. That means you're going to feel heavier. Have you been in an elevator when it starts going up? You feel a little heavier for a second? That's why. You're not heavier. G is the same. But you feel heavier because the normal force that's making you accelerate up is going to be greater than your weight. And that's what you actually feel, is that normal force. So, but what if the acceleration is down? Well, then your normal force has to be less than your weight. Now, what would happen if someone were to cut the cable on this and you were to accelerate at 9.8 meters per second squared in a downward direction? That would be so much fun. The normal force would be 0. And so your weight is the net force acting on you, so you're accelerating at 9.8 meters per second squared. So you don't feel any normal force. And you feel as if there is no gravity at all. Until you hit the ground and you have this massive, massive upward normal force as your body is crushed on the floor of the elevator. And then you don't have to finish your physics homework. Yay, there's always a silver lining. All right. Okay, so there's a problem like this on the test. Okay, problem number 4. Number 4, I'll just draw that little sketch for it. Something very similar. I've got a big crate. There's friction. And I've got someone pulling this way, and I've got someone pulling this way on this crate. So when you draw the free body diagram of this, I've got two, I'll call this F1 and F2. So I've got 2 applied forces and a friction force, and you have to handle that. Well, is that a big deal? If you know how to use the procedure, it's not. All it does is that now you have 2 applied forces instead of 1 to add when you sum the forces in the x direction. Okay? So if I were to sum the forces in the x, well, let's draw the free body. Let's be complete here. Here's the free body diagram, right? You're going to have this object. You're going to have F1. You're going to have F2. Let's say it's moving to the right. That means you're going to have a force of friction. And let's say constant acceleration, I don't know. Let's say A. And so if you sum the forces, you call this the X and this the Y. So, okay, I got F1 minus F2 minus the force of friction equals MA, right? That's if I sum the forces in the X direction, I get MA in the X direction. So you just work the problem that way. And in order to get the force of friction, what do I need to know? I need to know what the normal force is, right? Because the force of friction, am I still on screen? No. Force of friction equals mu times the normal force, and you go, well, what's the normal force? Hey, look, here's mg, and here's the normal force. Oh, the normal force is just equal to the weight, and so mu mg equals the force of friction. Plug that in there and solve for your unknown.
So the normal force is equals the weight when there's no y activity?
Right.
Okay.
Yeah, and that's a great point. If you look in this problem, the elevator problem, the normal force is what's changing, right? The normal force isn't just supporting your weight. It's also, if you're accelerating up, it's adding extra force to allow you to accelerate up. Or if you're accelerating down, it has to be less than your weight to give you a net force down. All right. Problem number 5. Okay, and I'm going to give you some hints on problem number 5. Again, a crate. But let's say I give this crate an initial velocity. V naught equals, I don't know. I don't want to use the same number. You know, let's just say it's 10 meters per second. And it's sliding to a stop. So that means the velocity over here is going to be 0. So, maybe, I don't know, this is what's given. And again, I can create, what are you trying to find? I don't know, I'm not going to tell you. You can find, what is mu? What is the acceleration? Maybe I give you mu, what is the acceleration, and how far will it slide? There's all kinds of variations on this problem. But here's what I want you to know. Draw the free body diagram of this crate. So there's the crate. What forces are acting on it? You tell me right now. What are the forces acting on this crate that's sliding to a stop?
Friction.
There's a friction force. Normal force. What else?
Force of gravity.
Force of gravity.
That's it.
Anything else? Excellent. Okay. And I'm glad you said it, even though I'm going to correct it. A lot of people will say, hey, this thing is sliding to a stop. So, and a lot of people will want to add an applied force to this. Some kind of pulling force? No. Don't do that. If it's sliding to a stop, there is no applied force. It's just sliding to a stop. Now, somebody had to apply a force to it, right, to get it up to that speed, but we're looking at it after it fell off the truck or something, or somebody released it. Maybe this is a, that would have been better than what I actually can. What if this was like or what do you call it, a stone from my favorite winter sport on the Olympics? Curling, right? Somebody pushes on this, pushes on this, pushes on. Have you ever watched curling?
Yeah.
Raise your hand if you've never seen curling. Raise your hand if you've never seen curling. Oh, you've all seen it. Oh, good. Either that or you're asleep. Yeah, it's great. This guy pushes on this little puck, and then he aims it, gets a speed, and then just slowly releases it. Now, when he releases it, or she, when it's the stone, I think they call it the stone, is released, the only force acting on it in the horizontal direction is this force of friction. A little bit of air resistance, but let's neglect that. And so there's no applied force anymore. So, hey, on this problem number 5, don't add an applied force or a pulling force or something like that. If you do, the problem is not solvable. Yes?
What if you make the applied force 0?
Yeah, well, then it's solvable.
Oh, okay.
That's kind of what I'm saying here. The applied force is 0. Yeah.
Okay.
Yeah. Okay. And number 6 is a qualitative, it's a question, and you have to answer the question, but it has to do with Newton's laws, Newton's 3 laws. So make sure you understand the law of interaction, the law of acceleration, and the law of inertia. Yes?
Do you have to know them in order? Like, do you have to know this law is this?
No, you just have to be able to apply them. If you say the law of, the order, it's kind of nice to know the order, though. I don't know why. And that's the exam.
And then also, if the crate has wheels, we assume that it has no friction. That's what I got from
Yes.
Okay.
Yeah, if I put it on wheel, I'm not going to try to fool you with wheels and friction. Now, there is an exception to that. What if somebody slams on the brakes and they block their wheels up? Now you've got sliding friction or kinetic friction that's trying to make you stop. And that's a possibility, yeah.
Okay.
That is all.